the second part of any series.
Thanks again to the other organizers for inviting me. Last time we turn it on. Is it on now? Yeah. Okay. So last time we saw that there's this strong coupling. Fixed point. Of the KPZ class, which presumably, if you have things like the KPZ equation, they're sucked into this universal fixed point by this 1, 2, 3 scaling. So on large space-time scales, the infrared limit is this universal fixed point, and there's this Gaussian fixed point. And there's all these other models in the class, which also presumably get sucked into this thing. But this thing is a integrable Markov process, so it has completely integrable. It's a Markov process with completely integrable. Transition probabilities. So last time I described those transition probabilities, they're Fredholm determinants of certain operators. Okay, so how is all this done? Because there's a special model TASEP, plus a couple of other special models, for which one has exactly the same thing. They are completely integrable Markov processes. Well, Markov processes with complete integral transition probabilities. So the way it's done is we compute the transition probabilities of TASEP and then pass to the limit to get these formulas. So what I'm going to show you today is the formulas for TASEP, which are similar to the formulas for the fixed point I showed you, and the fixed point formulas are just obtained as a limit. Now the formulas for TASEP, of course, are a little bit harder to write down because they involve lots of discrete things. And okay, so there's a formula. There's an exact formula for the transition probabilities of TASEP. Now, one thing, I could just write down the formula, and at the level of TASEP, the formula can just be checked because you have a infinitesimal generator for TASEP, so the Markov transition probabilities just have to satisfy the forward or backward equation, which in this case are the same equation because of the skew time reversibility. And you have the formula, and you can check. So I could have given the talk by showing you the formula and just check. So we have such an article, we can do that. It sort of looks like it was written by a computer. After a few hours, you can convince yourself that it's true, but it's almost impossible to see in a short amount of time. It's just some sort of black magic. So let me show you how it was really done. At least you can get some idea. Okay. Okay, so we're going to solve TASEP. Now, first of all, we're not the first people to have solved TASEP. TASEP was solved a long time ago by Günther Schutz. 97. Okay, so what Schutz did is he has a formula for TASEP with n particles. But by the way, everybody, I'm assuming it's the same audience. Should I say what TASEP is? Okay, sorry. So TASEP is this model where you go, the height functions are just going up or down by 1 at each step. The height functions are simple random walk paths, and the entire dynamics of this thing is that the hills jump to valleys at rate 1. That's the dynamics. Okay? Actually, the TASEP we're solving is a little bit not this. There's a rule that after a while it has to go down. So it just goes down after a while. Okay? Now, you could just, there's a way to map this thing where you call the ones that go up particles. So we'll call this particle x0, and this particle x1, and this particle x2. This is particle x3, x4, x5, etc. Okay? So it's just a one-to-one map. So they're called particles, and the reason it's called TASEP is these particles are just doing simple random walks to the right, but they're not allowed to jump on top of each other. They're doing it in continuous time, and if there's somebody in the way, they don't jump. So that's TASEP. So you can either think of it as the particles or the height function. It's exactly the same thing. And of course, what happens when a hill jumps to a valley is just that this particle jumped to the right and had nobody in front of it. Okay? So you can think of it as particles or hills, and that's the TASEP. So that's the TASEP model. Okay? So what Schutz did is, if you start with particles in positions x1, 0 to xn, 0, so there's only n particles, then there's a probability sub that x1t to xn t is equal to x1 through xn. Okay, I hope, don't worry about the notation too much. If you have n particles, you can calculate the n-step transition probabilities, and it's given in terms of an n by n Fredholm determinant. And there's some functions. J, this is n by n. Okay. Of course, these aij's depend on the x's and t's, everything like that. The problem with this formula is that's not what we need. We need a formula for an infinite number of particles and then a time t later to know where 1 or 2 or 3 of the particles is. Because knowing where those 5 particles is will tell you what the 5-point distributions of the height function are. There's a simple translation from the x's to the height function. The x's are sort of the inverse function of the height function. Okay? So the problem with this is that you need the first n to be infinity and the second n to be 5. And you can see that it just involves enormous summations over this thing, which is no use, and nobody knew what to do with this formula. Okay? So it was solved, but solved in a way which wasn't helpful. It was actually Sasimoto who understood what to do. So Sasimoto realized, I'm not, maybe okay. Maybe I should actually tell you what's the guy in there, just for fun. Okay, because you'll sort of see these things come up later. So the function inside there, what goes in this n by n determinant, they're contour integrals. C to the xi minus xj 0 minus 1 e. That's the ijth entry of the thing. This is integrated over a little circle around 0. Okay, so these are the kind of things you get. Now, what he realized is that these functions have some sort of functional relationship. In particular, they sort of sum into each other. I'm not going to write it down. There's a functional relationship of those functions which allows you to do row reduction. And when you do row reduction on this thing, you end up with a sum over a set of Gelfand-Zetland patterns of another determinant. And that thing is a signed determinantal point process. And if you have a signed determinantal point process, then you can write down a formula for the probability that the x's at some few points are less than something. That's the Armada theorem. So let me just tell you the result of all that, which would take 2 hours to describe. Okay. So the result of all that is a theorem of Borden, Ferrari, Sasimoto, and Prof. Sorry, they're not in order. From 2006, and it says the following. Okay, so the particles are initially ordered. Okay, so here's the names of the particles. I'm sorry, I changed the way they're. Okay, there's still n particles, but this is going to be very weakly dependent on n. Unfortunately, it takes a minute to write down. You'll see. Okay, so these guys are ordered, and we want to know the probability that at time t, the njth particle is greater than or equal to aj. This is what it gives you for just a finite number of j equals 1 to m. M's much less than n. Okay? This is given by something which will be familiar from last time, minus k. And k is an m by m determinant, m by n operator. And this is on the product j equals 1 to m of little l2 of aj to infinity. So this is already looking like it has the form of last time. And the important thing is what's the k. Okay. So k is a operator which is given by a kernel, so defined by its integral kernel. Well, now it's a sum kernel, of course, because all integrals are sums. And it's m by m, so it has an ijth coordinate. And the ijth coordinate is given by the following. So sorry, there's going to be a lot of notation. That's what happens with discrete stuff. There's a matrix Q to the nj minus ni times the indicator function I is less than j plus 2 nj psi ni minus k phi. Okay. So that's the formula, but I got to tell you what all these things are. Okay. Q's a weird thing. It's just the indicator function that u's greater than v as an operator, as a matrix. Psi kn are basically sorry, I'll call it X. Psi kn are a version of these guys. They've been rewritten a bit. So there's some contour integrals. So gamma 0 is a little circle around 0. And now stuff is going to be familiar to anyone who's ever worked in exactly solvable KPZ stuff. Those are the psis, and you're supposed to build your integral kernel out of the psis and certain phis. And so now here's the problem. So gamma 0 contains the pole 0 but not 1. So these sort of things are actually important because all these contour integrals really are ways to encode certain series. Okay. So that's the formula. The problem is, what's the phis? The phis are given not explicitly. The phi's are the biorthogonal pairs to the size. They're the biorthogonal pairs. And the only other condition is that they're supposed to be polynomials. Degree less than or equal to n minus 1. Okay. Okay. So that's what you get. And of course, everyone can see the problem. What are the phi's? Now, so don't worry about all the funny little definitions. They're size and they're explicit, given by some contour interval. Don't worry too much about that. But you have to figure out what are the phi's. Now, just to make
Are unique or
they're known to be unique. Yeah.
Sorry, when you say polynomial in X?
In X. Okay. So I want to try to put this in a slightly, make it look a little bit more familiar. If you take the following measure mu z, u minus t factorial. It's just the Poisson measure. Okay? Then there's orthogonal polynomials with respect to the Poisson measure. They're called Charlier polynomials. Okay, so you can find these polynomials, and they're like discrete versions of the Hermite polynomials. Okay. In fact, except for this shift here, that is basically the size. Okay. Now, so if you're given these Charlier polynomials, and then what you're asked is the following bizarre problem. You're asked to shift is shifted by the x's, by x. Okay, let me see if I can get this right. 0, I think, k plus k. Okay, if I didn't get it right, it's morally right. Okay, so what you do is you're asked to, you're given certain orthogonal polynomials, and then you shift one group of them. Well, it's actually with the measure, which is a bit annoying. And now you're asked, what are the biorthogonal things to that? Well, of course, you say, oh, that's easy. I'll just shift the other, shift the other ones, and they'll be biorthogonal. Think about it for a second. It doesn't work. Of course, you get the indicator, if they're the same number, you get the indicator function, but otherwise they're not biorthogonal anymore. Okay? It's such a simple problem, but there's no obvious way to solve it. Unless you're lucky, unless x0k is minus k, then I think everyone can solve this problem. Right? So if x0k is minus k, then you actually know what's the phi's. The phi's are just the size, basically. Well, not the size. The size, you just get rid of this thing, and then you know what they are, and then you can construct the kernel, and you're home free. So now you know what TASEP is if you have a filled block of particles. You can compute the kernel. Okay? Or in the language of Einhard Meta, you can invert the correlation kernel. So all of this is just inverting a correlation matrix, which is the new thing here. Okay. So I just want to say that again. If you have a solid block of particles, you can solve this problem. And now you can take that solid block, you can get n go to infinity, and that means that's how you solve the corner model. Okay, so that's how the corner, okay, it's equivalent to how the corner model was solved. So this isn't actually exactly the first way that the corner growth model was solved. The corner growth model was first solved by Johansson, and then you guys maybe? This is a slight reformulation which makes it a bit more clear and does it in general. Okay. Okay. So from that, that means that for the corner, you can get a formula. So you get a formula for narrow wedge. So this gives a formula. Oops. And now I'll put in the initial data. So the initial data here is a narrow wedge at 0. So that's just the function which is 0 at 0 and minus infinity everywhere else. The narrow wedge at 0. And now this function of x is the Airy process minus a parabola. And you get a formula for that. Okay, so in other words, you can compute the kernel, and so you get a formula for the endpoint distributions in x of this function for every t. Okay? The t is not terribly important because it's, you can just figure out it's t to the 1/3 of the times at t equals 1, so you know what the thing is. Okay. So it's enough to just take t equals 1. Okay. Okay, you get a formula, but the formula is in terms of an n by n matrix valued operator. So there's another ingredient to this whole story, which is that there's another formula, an earlier formula, which was discovered by Herbert and Prohofer, which is equivalent by a big algebraic machine, which I won't show you. Bond version of the formula. This will be very important for us. Okay, so here's the formula. So this is the formula for the probability that h of 1 x delta 0 plus x squared is less than or equal to xi is less than or equal to ai equals 1 to m. Okay. So it goes like this. Should I call it n? You take the Airy kernel, and now you take projectors on minus infinity onto a 1. Oops, sorry. E x1 minus x2 h projector minus x2 minus x3 h projector to an to the xn minus x1 h k Airy. Okay. H is the Airy operator minus d squared plus. Okay. I think I described everything. Okay. So the nice thing about this formula is that formulas like that involve the size of the space is increasing with little n. Or I could have called this m. With the number of points you're looking at. You have to look in bigger and bigger products of L2. But here, the whole thing is on one L2 space. It's a d-extended formula. I think when you guys got this formula, you thought it wasn't the right formula, and you turned it into formulas like this. But these formulas are lovely because they're on one space. And so they're very good for passing to n goes to infinity limits.
We want to prove tightness of the area process. We want to know that it has continuous sample paths. And then somehow we realize that we have to use this formula.
This formula is, yeah, good for that, yeah. That's right. There's like two versions of these formulas, and this one's better for some things and that one's better for other things. And it's a little bit hard to tell which to use. You'll see in a second why this formula is so important for us. Okay. So anyway, but it's just an algebraic computation which goes from the formula like that to this formula. Okay? Now, the first thing, well, this is just my taste. You don't have to do it. I don't like that h is minus d squared plus u, and that there's a parabola here. So you just do a parabolic shift of the whole thing. So a parabolic shift takes h to minus d squared. It just gets rid of the u. So you just do a parabolic shift of everything, and now it's just the heat equation. Okay. So now you want to look at this formula and see what it's trying to tell us. So here, the x's, if I didn't say so, the x's are ordered in backwards order. So x1's less than, no, x1's greater than x2. Okay. Okay. No, sorry, the other way around. The other way around, and it goes to minus d squared. Right, okay. So now, this is a little bit of heat equation going forwards. If h is minus d squared. And you keep applying the heat equation a little bit. You keep applying the equation, except for the end, where you apply the heat equation backwards for a long, over the entire interval you were looking at. Now, what we could do is we can just take an interval from minus L to L and chop it up into tiny little pieces and let those be the xi's. So it's x1, x2, etc., etc. Okay. Let n go to infinity. And then the formula reads the following. So now the a's, we just let ai equals some function g of xi. So now you've got some function, and you're trying to see if the area process is less than or equal to some function at those points. And so you get, without too much trouble from this formula, the probability that the area process this is the area process minus a parabola now because of the parabolic shift is less than a function g on minus LL is given by the following formula. So this is just a fine mesh limit of the formula there. Determinant I minus d cubed over 3 minus L d squared P G minus infinity to 0. You get this formula, which should look a lot like the formula yesterday. The only problem is, it's not a problem. this guy's upside down. Before we were hitting our initial data from above. And now you're hitting this G from below. So I'm going to now differentiate hit operators by calling them epi and hypo. So the epigraph of a function is everything above the function. And what you have to do is hit that closed set, which is the epigraph. G is supposed to be now a lower semi-continuous function. Okay, so this guy is just the old operator upside down. And here's the e to the, or I could write it like this. Here's the thing I wrote last time. And these are just area functions. These are just surrounded by area functions. So you get this formula. And so now it's very clear where the Brownian scattering operator comes from. Okay? This all goes to infinity.
So why did the L2R suddenly become the L2 minus infinity 0?
Because I did some manipulations. Okay, let me tell you those manipulations. So you remember K area is basically area function and then projection from minus infinity to 0, and then an area function. Okay? So I reordered the whole thing by taking those area functions. There they are. Those are the area functions. And then I have a projector from minus infinity to 0, which now becomes in the L2 space. Okay? And then I just reordered them by going around. Also, you see here, this was the main reason I wanted to do that was this is e to the 2l, e to the minus 2l d squared. So it only appeared on one side, but I want to appear on both sides symmetrically. Otherwise, you're sort of focusing on the end, and and it just goes off to infinity. Okay. All right. Okay. Now. Okay, so we're getting there. Now, of course, this is just a formula for the area process. It's a formula for the one initial data, the narrow wedge. And we want a formula for everything. So now we use the skew time reversal invariance. So remember, by skew time reversal invariance, this is also equal to the probability that the fixed point at time 1, starting with minus g, is less than or equal to minus delta 0. Minus delta 0 is just an upside down narrow wedge. So this is just the same thing as saying the probability starting with g that at 0 minus g, this is less or equal to 0. Okay? So skew reflection invariance tells you that if you know the general solution starting from a narrow wedge, then you know the one-point distributions starting from anything. Okay? And now I have to get multi-point. So to get multi-point, you just notice the following thing. Okay. So, well, now I'm going to pull a hat out of the bag. You check the following. These functions have the property that q to the n minus m of psi n minus k is equal to psi m minus k. So what the q's do is they shift these psi's around. This is the analog in this discrete world of the functional relation for the Hermite polynomials. Okay? What that means is that I'm losing space to write it. That means that the extended TASEP kernel, so X just stands for the matrix version of the 1 point version. So 1 point things have a kernel which is just 1 by 1. To go to the matrix version, you just look at the version where the ends are the same, and all you have to do is sort of conjugate by the q's. Where k is just the diagonal version. Okay? But now that means I can just guess what's the full fixed point formula. That tells you that at the fixed point level, so you see now we've got the 1 point kernel at the fixed point level, because we went at 1 point. But if we want multi-points, we just want an n by n kernel version of that, but all I should do is conjugate by whatever the limit of the q's is. Does that make sense? But what's the limit of the q's? Well, the q's, they don't look like they have much of a limit. Where are they? Here. Doesn't look very, well, they do have a limit, but let's not worry. There's a better way to do it. Okay, so what's the limit of the q's? If you take the formal limit of the q's, you get the wrong answer. So you have to do it a bit carefully. Okay, so we learned that if we can figure out what's the limit of the q's, then conjugating by the limit of the q's should give you the guess of the fixed point formula multi-point. Okay? Now, the q's don't look very good, but the equation is invariant under conjugations, because the determinant of I minus k is the same as the determinant of I minus a k a star. So let's conjugate by multiplication by 2 to the u. Well, that does the following thing. It doesn't do much, but it turns this into 1 over 2 to the u minus v. And now I know what q is. Q is the generator of a geometric random walk jumping down. And if you want to know what the limit of the geometric random walk is, it should be the limit of a random walk. So we should be scaling everything so the limit of these random walks are Brownian motions. And so the limit of that formula is just that I take, oh, so this guy went to kh, and I should just conjugate by the heat kernel, which is what I showed you last time. And so you get the KPZ fixed point formula. Okay? Okay, so now, of course, that's just a guess. So the way you solve TASEP is by solving the fixed point. But how do you prove it? You can't prove it because you don't know what the fixed point is yet. So now you go back to TASEP, use your guess to figure out what are the phi's, check that it's correct, and then take the limit back and see that you got the right thing. Okay? So the question is, what are the phi's? Now, we know that kh comes from a hidden kernel. So, yeah, but when I turned it around, it's a minus g. So when it's a minus g, it now becomes the hypokernel. So I'll draw it like that. So there's this minus g. And I know it comes from a hidden kernel. So I was starting from here, u, and I go to v. And you were supposed to hit and go there. Okay? So now you have to try to guess what are the phi's. And it's not so hard to guess. If I hit, then there's a first time I hit, tau. After I hit, I have a free evolution to get to v. But the size are free evolution, q. So that means that the phi's should be the probability that's starting at u the first time you hit is k. Okay? And I've got 10 minutes, I'll show you it works. Oh. It's kind of fun. The first guess works. Okay, so in other words, we guessed that the phi's should be the probability starting, they're functions of v. It's the probability starting at v that the first time you hit the curve is now the x's, is at k. Well, you have to set that up as a probability problem, so I'll do that. It turns out here you want to use the transposed q's, which is just the ones which jump in the other direction. They jump up instead of down. It's a rather nasty probability problem to try to calculate the probability that the first time you hit is at a certain time. It's a very singular problem. So we're going to solve from k. You have to actually solve the heat equation backwards from k to do that, with a zero boundary condition along your curve. So the final condition, h n k z. Well, it's funny because it's geometric random walks and you're allowed to hit anywhere above the curve. So it's 2 to the minus z minus 0 n minus k. N here is just a parameter which says where along the curve you're looking. So it's not really part of this problem. It's just a parameter. Okay. And then for L less than K. That's the problem. You have to solve if you want to know the hitting probability of the hitting density of a curve by a random walk. Okay? Is the backwards heat equation. And the theorem is that H and I'll show you the proof. Once you guess the thing, the proof is 3 lines long, and it always works. You'll see it. It's so soft it has to always work. I just want to point out that H, K, N, L, Z is the probability that the transposed walk, I call it B transpose, it's just the walk that jumps up instead of down. L minus, starting at Z, the first time to hit the strict epigraph of x 0 n minus m as in the parameter m. So n is just a thing to tell you where you're looking, is equal to k. Okay. So this is just, that's elementary probability to check that it's that. Okay. What's a little bit unusual is to check that it works. So, actually, 2 changes a little bit. 2 changes to something like 2 to the u. This is a polynomial because of the conjugation. And if you want to check that that's true, actually you can just check it by marching backwards. Well, it started out to be a polynomial. The polynomial fixed constant. Check if you go back 1, this q. Oh, I should show you. Q is invertible. Q has a simple inverse. So Q inverse is just Q inverse u v is 2 times 1 u equals v minus 1. So it's easy to invert Q. And so you can just apply Q transpose, and you'll find out one iteration gives you a polynomial of degree 1, or the next gives you a polynomial of degree 2. It's very, very simple to see that. So the interesting thing is that they're bioorthogonal. Okay, so this is the sum. So the first thing to do is just check what the size are in terms, the size can be calculated because of this formula. You just keep marching back until the integral is just computable. It's easy. So you can just check that the size are e to the minus t over 2, 1 plus grad minus z1. And now I have q to the minus L Z1 X0. So that's actually the psi. You can just compute this by hand. But now you have to multiply it by h, k, n, 0, z2, e to the t over 2, 1 plus grad minus z2 z, and compute the sum. Okay? But it's easy because it's just the inverse operator. So that just says, just contracts the z1, z2 variables. So you just get the sum over z of q to the minus L z h minus L h k z, which is just a way of writing q transpose minus L of h k n at 0 x 0 minus L. Right? But this is just from the formula hkn L of x0 and minus L. But that's either 0 or 1, depending on whether you that's it. So that solves TASEP. And the only thing left, there's one little twist to the story, which is that this is only true for z below the curve. For z above the curve, it's just some polynomial extension of those things. But you might want to know which polynomial extension, and so you just check. And so you see, this problem, you could solve it on the whole space then it's only below the curve that it's actually hitting probabilities. Above the curve, it's just something else. It's a polynomial, but what polynomial? It's the following. So you define a different version of Q, which is sort of polynomial extension of Q. Minus B minus 1. I'll tell you what these things are in a second. Where that thing is the Pockhammer symbol. So in other words, the Pockhammer symbol is just a polynomial extension of the binomial coefficients. Okay? So this is just a polynomial just defined by that for integers k. K, positive integer. Okay. So that's your extension of Q, and the real formula for the phi's involves the extension of Q instead of the Q, and so I'll just tell you what the KSEP kernel is. So the answer to that problem is the TASEP kernel UV. Now I just have to write the 1-point kernel, because you know from that formula how to get the matrix version of the kernel just by putting Q's on either side. It's just e to the minus t over 2 grad minus q to the minus n. As an operator, now I have to write this as a sum over z, because you'll see why. Now I have the expectation starting from z of this random walk, which is doing geometric walks up, of q bar n minus tau e to the t over 2 grad minus of b tau t. So it's that geometric random walk jumping up where it hit v. And that's the formula. So that gives you the transition probabilities of TASEP. And there was one thing I wanted to say. As you can see, the evolution in T is trivialized at the level of operators. So TASEP is a Markov process with completely integrable transition probabilities. And just taking the limit of that formula is all the magic that we saw yesterday. Okay, I'll stop.
Questions?
One question, so you arrived, at this beautiful formula for the TASEP, but then going to the limit, you would think that there should be an infinite number of sort of, complicated, to really go to the fixed point, and from this formula, there should be still sort of complicated stuff going on, or is that sort of something which...
But you see, it's unbelievably well set up for taking limits, because it's not one of these things where things are fighting each other. Okay, I had to write down all the scaling. The scaling takes a blackboard just to write down what scalings you want to do to this thing, and so I'll save you that. But all that happens is that the geometric random walk converges to a Brownian motion, and this converges to that thing I wrote, the e to the t over 2 d cubed minus x d squared. It's just simple. Each one's converging to the right thing, and most of them are very easy. The only thing that's hard to prove is the trace class convergence. Yeah, but point-wise, it's just obvious. Yeah.
In the equilibrium situation, like for instance for 2D easing model, if someone gives you the explicitly, there is a clear notion of what it means to deform it in some direction. Is there something similar here?
That's a very good question. My answer is that's a very good question. I mean, it's too new for us to have done things like that. Did everyone hear the question? One should try now to deform it and and look at things nearby, but we haven't had time to do that. So, I'm just reporting on things which are too new for us to have time to do that, but of course that's the right thing to do.
Okay.
Yeah, I mean, so do you have some idea about the generator or not?
The generator of?
Of the limiting object.
Well, you see, the problem is that if you write down the generator, you can't find any functions in its domain. So that's the big problem.
But I mean, if you are given that formula you wrote, no, you check by hand in the discrete setting that it satisfies the. I mean that.
No, it's a way. So at the TASEP level, I can just check
Yeah.
that it satisfies the forward equation.
Yeah.
At the fixed point level, it's not only that I can't check, I can't see it formally why it would be true. Yeah. If you take the formal generator and you try to apply it to the fixed point formula, I can show the problem. It's really fun. Even if you're willing to be very, very crude, you don't see why it's true.
But why would be this formal generator? I mean, what would be this formal generator you?
Of the fixed point?
Yeah.
Oh, it's just, I mean, you know what it is. It's, I mean, good luck with it. So it's a operator on functions of heights, right? It's the integral of a quarter dxh squared d by d hx f dx.
Yeah, but for example, can you prove in some sense that okay, maybe you cannot construct the generator, but the process satisfies the equation in some weak sense, for example?
How could you?
No.
What is that?
No, but for
You see, in
for Borg.
in your stuff.
No, for burgers. No, if you take the point of view of burgers.
No, it's no better. It's no better. It's the same problem. You see, in your stuff, you make sense of objects like this. Okay, maybe one has to subtract infinity. Okay, fine. You make sense of that by writing them in terms of the bunch of Gaussian integrals, right? To the extent that the rest of it is okay. I have nothing like that.
Yeah.
So how am I supposed to make sense of the thing? Of course, it's a good question. Maybe somebody here is imaginative enough to solve it.
Okay. So let us thank to all speakers of this morning.